All right, welcome to the next chapter here. We're going to be moving into chapter 2. I need to put my share screen here. And as we move into chapter 2, sorry, you guys probably thought that it had frozen. Let me just make sure. Let's just see if this works. All right, then let me hit present from the beginning. Okay, good. All right. One would think that I would just delete all this and start over, but I'm not gonna do it because I don't have time for that. Ain't nobody got time for that. Anyway, so we're heading into chapter 2. As you can see, we're going to go into chapter 2. Chapter 2 is about chemistry. Now, what you need to understand about chemistry, and I know that a lot of you have already had a chemistry class or are planning on taking a chemistry class. Some of you may be currently taking your chemistry course. There are some really important parts to chemistry that relate directly to what you're going to be doing as medical professionals. However, there's going to be quite a bit about chemistry that you don't really need to understand or know as far as the purposes of this particular class is concerned. And so I'm going to go through some of this stuff, but I'll tell you kind of, okay, now this is going to be important and this not so much. And so most of what we're going to learn in chapter 2 is actually directly applicable to what you're doing in this class. But there will be a couple of things that'll be a little bit more, I don't know, some foundational knowledge that you need to understand some of the other chemistry that you do need. So let's kind of move right in. Of course, matter has 3 forms, right? You've got solid, liquid, and gas. Those are all important, and it's important to understand what they mean as far as how they work in the body. Your body is going to be doing a lot of liquid exchange, but there's also a fair bit of gas exchange as well, and taking gases and converting them into an aqueous solution, putting them into a liquid form essentially. And so it's important to recognize those. It's also important to recognize the different states of matter. So well, not states. I should really kind of reevaluate where I'm going with this. You're going to have atoms. You're going to have this matter that's going to be organized into atoms and molecules, and that is actually fairly important. You guys need to understand the difference between an atom and a molecule and what a molecule is. Of course, the atom is the smallest particle that exhibits any sort of chemical properties, and the smallest particle that does exhibit specific properties is going to be an element, right? So we've got a periodic table. There are 92 elements on our periodic table. And so an element is going to be like carbon, nitrogen, oxygen, phosphorus, sulfur, chlorine, calcium. There's some sodium over there, some potassium, gold, silver, copper. These are elements because they're atoms that are organized sort of in their purest form. When you have a bar of gold, you only have a bar of one type of atom, right? It's pure. It's one thing, and there is nothing else. But and the same with copper. So if I take copper, if I've got a copper pipe, I have a pipe that is made of only one type of atom. But if I take that copper and I add a little bit of tin to it, now all of a sudden I've got, I think bronze. I think that's what bronze is. Bronze is a metal, but it is not an element. It is made up of 2 different types of elements that have been sort of, mashed together in molecules. And that really is kind of important. Your body your body is going to be using oxygen molecules, but it's going to be breaking down those oxygen molecules into atomic constituents. It's going to be breaking those apart for use. And so, you know, the common elements that we use, that we see in the body, of course, are listed right here. You can read those. I don't need to go on. You guys got this, right? You should be looking at your book right now. It's figure 2.1 in your book, chapter 2, the first picture. Anyway, those are the most common elements: oxygen, carbon, hydrogen, nitrogen, all of that stuff. Now, your atom, of course, you guys should know this from high school science, high school chemistry, and atoms are composed of a neutron, proton, and electron. Neutrons and protons are sort of found in the middle of the atom. They make up the nucleus. A neutron has no charge, a proton has positive charge, and then buzzing around that nucleus, you're going to see the electron particles. And the electron particles are very small, highly energized, and negatively charged. So anyway, on the periodic table, I'm going to say that a lot. Anyway, moving on. This is kind of how I do my lectures in class too. It gets annoying. I'm sorry. You're going to have to deal with it. On the periodic table, we have chemical symbols. And that chemical symbol, it's unique to each element. Do we have one coming up? No, let me back up. So that chemical symbol is going to be right here on your periodic table. And it includes the whole thing. The number, you've got the atomic number for iron is 26. You've got the symbol itself right there, which is Fe. It's some kind of a Latin reference to iron. And then down here, we've got the atomic weight. And the atomic weight is going to be the protons and the neutrons together. In a lot of cases, in many cases, your protons and neutrons pretty well equal each other. If you have 8 protons, generally you're going to have 8 neutrons. That's not always the case, though. So, you know, that's something to keep in mind. Actually, it's not. You're not going to need to know that. So, I don't know why I'm doing it. Anyway, so there we go. The electrons have such a small amount of mass that they're not really counted in the atomic mass. It's really just counting the protons and the neutrons. So, let's see here. Moving right along, yep, your proton number is going to equal the atomic number. So iron had that atomic number of 26. That means that it has 26 protons. In a normal atom, you're going to have the same number of protons as you do electrons. And so if you have an atom of iron that is an atomic number of 26, it's going to have 26 protons, and then it's also going to have 26 electrons as well. Now, the neutron number generally is just going to be, it's going to be the atomic mass minus the atomic number. And so for iron, the atomic mass was like 55 point something. And then your atomic number is 26. And so 26, 55 minus 26 is something like, I don't know, 24 or something like that. And so that essentially is going to be what your neutron number is going to be. So, and then again, electron number is going to be equal to the proton number, except when you're dealing in things like ions, right? Cations and anions. Those are going to have a charge to them, so for example, sodium. In my class, in my face-to-face class, we talk about sodium, and I show this video. I can't really show you the video right now, but if you go to YouTube and you look up sodium explosion, you get some really awesome videos of people that just chuck sodium into water. Pure sodium thrown into water makes a real nice explosion, real big boom sort of a thing. And that's because sodium in its pure form is extremely reactive because of the number of electrons that it has buzzing around its nucleus. Now, we have to have sodium in our bodies in order for your muscles to work. We'll go over that later. Your body has a need, it's a survival need for sodium. So how do we take sodium in without it, you know, exploding inside our bodies and, you know, making a mess? Usually in my face-to-face classes, we talk about body parts flying all over. Anyway, the reason that sodium doesn't explode inside your body is because the way that we take in our sodium is generally through salt. And salt is an ionic bond between sodium and chlorine. But when those two molecules, or I should say atoms, when those two atoms bind into a molecule, they turn into ions. Sodium turns into a negative ion. Chlorine turns into a positive ion. And at that point, the reactivity of those two atoms is like gone. There is no more reactivity. And that's what an ion is. An ion is going to have either one or more too many electrons or not enough electrons. And so for sodium chloride, table salt, the sodium is going to have one extra electron, one more electron than it has protons. I think that the atomic number is 11. And so the ion for sodium, the sodium ion, is going to have 12 of the electrons and 11 protons, which throws off the charge. It winds up, instead of being a balanced charge, we have a negative charge because there's one extra negative particle. Whereas chloride, we should say, because it's now an ion too, it has lost an electron, meaning that it's got one extra proton. I think it's like 18 protons in a chloride ion. And so now it's got a positive charge, but because it's lost those lost or gained an electron, depending on what type of atom we're looking at, it could make it non-reactive, which is what happens with sodium and chloride. You can eat sodium, you know, a sodium ion, and nothing happens because those electron, that ionic component, has rendered it non-reactive. So, well, and that's kind of what we're talking about here is each atom is going to have these energy shells, right? The first energy shell of the atom, that very inner one, here, I don't know why I'm pointing. You guys can't see me point. This very inner one right here is going to have 2 electrons. Always 2 electrons on the very innermost one, okay? And then on the outer one, so this is the octet rule. On every energy shell outside of the first one, there is enough room for 8 electrons. Once 8 electrons are in that energy shell, we start on the next energy shell. We fill it up with 8. We start on the next one. And so depending on how many electrons are on the atom is going to determine how many electron or energy shells there are. But what you need to remember, this is kind of important as far as chemistry goes, is that you have 2 electrons on the innermost energy shell and 8 on every subsequent shell, okay? So isotopes, you don't need to know about isotopes, really. You can just ignore all the rest of this stuff. But essentially, it's where you have imbalances of protons and neutrons. So like carbon-12 has 6 neutrons, carbon-13 has 7, carbon-14 has 8. Carbon-12, I believe, is the most common isotope. So anyway, radioisotopes, I'm just not even going to talk about that at this point. It doesn't matter. You don't need to know about radioisotopes. You will use radioisotopes in a medical setting, but you can learn about that later. You can pick, okay, fine, here. The radioisotopes have more neutrons than normal, and so they're a little unstable, and so they lose these nuclear components. You know, they're like literally, you know, these neutrons are popping off of the nucleus in the form of high energy radiation. You can have alpha, beta, and gamma, well, gamma rays and alpha and beta particles. There it is. Half-lives are kind of cool. Isotopes generally have a half-life. It's the time for 50% of the radioisotope to become stable. It can vary from a few years, a few hours to 1,000 years. I don't know. We actually use this when we talk about carbon dating. We take something and we look at it and we think, okay, well, it's got this much of the unstable carbon and this much of the stable carbon. And so we can extrapolate from there how old it is because we know what the half-life is. If the half-life is 2 days and you have this much of the stable, then you know that it's taken, 4, 8, 10 days for that amount of stable carbon to be present in your substance. It's a little complicated and you don't need to know it. So, but here's why you might want to use radioisotopes, is we use them in medical imaging, right? They're used by cells in a similar manner to non-radioisotopes, except that we can look at them. We can actually see what's going on with these iodine radioisotopes. And so we can kind of see if the thyroid gland is taking up the iodine, and we can sort of look at, we can find nodules, we can find cancers, we can figure out whether or not your thyroid's working using these iodine radioisotopes, because we can see them, because they're putting out these radiation waves, gamma rays, or alpha and beta particles. So chemical stability and the octet rule. Let's talk about that. So I want to take my pen right here and I want to point at these things. So right here we've got hydrogen, right? I want you to look very closely at that and notice that hydrogen has one single electron. That means that hydrogen really wants to fill that energy shell. And because it wants to fill it so bad, it's going to be very reactive. It's going to be, cruising around looking for something to grab onto that next electron shell so that it can be stable. It wants to be stable. And because that first energy shell takes 2 electrons, it wants 2 electrons. And that's why hydrogen is so reactive. You take hydrogen gas, you light a match to it, and it will go boom. Which is what happened to the Hindenburg. I don't know if you guys know about the Hindenburg, but it was a giant German Zeppelin, and it crashed and lit on fire and just incinerated in seconds because it was full of hydrogen, and hydrogen is really, really reactive. Now, on the opposite end, though, of the periodic table, we have helium over here. Notice that helium has 2 electrons. Those 2 electrons mean that helium is completely stable. It's utterly stable, and it's not gonna react. Which is why you can suck up helium. You can inhale helium, and it's not really gonna hurt. It's not gonna hurt your body because it's completely non-reactive. It's got its 2 electrons, and it's not looking for any more. Now, it's not completely healthy for your body to inhale helium because it's going to deprive you of some oxygen. So it's not something you want to do all the time, but it's fun to do every once in a while at a party. Now we come over here to lithium. Lithium is going to be what we call one of the earth metals. You got lithium and sodium and potassium. They literally, they're metals when you look at them in a pure form. Note that lithium has 2 electrons on that inner ring. Stable, perfectly stable, in good shape. However, lithium's only got 1 on the outside. And so lithium is going to really want to get rid of that 1 electron, and like that. It's going to really want to get rid of that 1 electron, because if it can get rid of an electron, all of a sudden it can be stable. Once that electron goes away, it is now non-reactive. And so lithium is also very reactive. We come down here to sodium. Right here, sodium, you're going to notice we got 2 on the inner, and then we've got 2, 4, 6, 8 on the outside. Octet rule, okay? It's the octet rule. Once we hit that magic number of 8 on the energy shell, then we go to the next one, right? But note too that sodium's also got 1 little electron buzzing around which makes it very reactive. It wants to get rid of that one electron so that it can be stable. On the flip side over here, if we come over here to chlorine, chlorine is stable right here. It's got its 2 on the first one, it's got its 8 on the next one, and it's got 2, 4, 6, 7. It's only got 7 on the very outermost one. Again, really reactive, because every molecule it encounters, it wants to pull that other electron off of it, right? Which is why chlorine and sodium are a match made in heaven, because chlorine wants to take an electron and sodium wants to give it away. So, you know, they come together and chlorine's like, hey, can I have that extra electron? And sodium is like, yeah, you can have it, I don't want it. And so they you know, chlorine takes the electron, and now all of a sudden sodium has a negative charge. And because chlorine is positively charged at this point. No. Oh my gosh. Sodium is positively charged, and chlorine is negatively charged. I've got it in my head a little bit wrong. Chlorine is negatively charged. We got a positive, got a negative, and then they become attracted to one another and form a bond. We call that ionic bonding. Over here, I do want you to notice that we've got on this side what we call the noble gases: helium, neon, and argon. These are all gases that have filled their energy shells. They're completely stable. Neon, neon doesn't really do anything. It will react to an electric current, but other than that, it's very stable. It's non-reactive. So then we get to chemical compounds. Chemical compounds are going to be a stable association between 2 or more elements. Ionic compounds are formed into ionic bonds. Let's see here. Yeah. Oh, I'm going forward. I wanted to go backward. An ion, like I said, is an atom with a positive or negative charge, and they do some major stuff in your body. You have to have sodium. You have to have potassium in order for things to work the way that they need to work. In most cases, we're talking your neurological pathways. They use a lot of sodium and potassium, and then also your muscular energy pathways are also using potassium and sodium. So let's see here, losing electrons and the formation of so you got cations and anions. Cations are ions with a positive charge, anions are ions with a negative charge. And then you got polyatomic ions. That's going to be an anion that's got more than one atom. It gets a little bit crazy, it gets a little bit complicated. Bicarbonate is one. We'll be talking a little bit about bicarbonates, but you don't need to know too much about polyatomic ions. So ionic bonds, I mentioned that's formed when you have 2 differently charged ions, like a positive sodium and a negative chloride, I should say, and those 2 those 2 charges create opposite attractive, or similar, I should say, similar attractive force. They become attracted to each other. It's like a magnet. Remember how a magnet's got a positive and a negative pole, and when you put the positive and the negative poles near each other, the magnet comes together. But if you put the same pole, if you do a negative and a negative pole on the magnet, they repel one another. They literally push each other off. You can feel that electromagnetic force when you try and push those magnets together. When I was a kid, I used to try and get these magnets, and I try and force them together. And it was kind of hard. I did it just a couple times on specific shapes of magnets, but it's tough. It's tough to kind of get those 2 things pushed together. So anyway, yep, there's an ionic bond right there. So sodium donates its electron to chlorine, and now sodium is stable, and now chlorine is stable right here and right here. And now they've got these attractive forces. They've got these electromagnetic forces that cause them to form together. They get put together, and it forms a very specific crystal structure that forms up into a cube. you guys have seen, I hope, you've seen microscopic images of salt, and it's cubiform. So covalently bonded molecules, this is where the electrons are shared between a couple of different elements. This happens far more often. So an ionic bond, if you think about salt, if I can take my salt, I can take a block of salt, solid salt, and I can put it in water, and that water is going to dissolve my salt. And it's because the water is a solvent, and the molecular forces between water and the sodium chloride are strong enough to pull the sodium chloride apart. They literally destroy that ionic bond because the water has some hydro forces, oh shoot, is it hydrostatic? No, it's not hydrostatic. Hydrogen bonding forces. Anyway, the water's got some forces that will actually pull apart those two elements. And so when you drink a glass of salt water, you're actually not really drinking salt water, you're drinking water with that has sodium and chloride in solution. The water has actually pulled apart, dissolved those atoms. Now in a covalent bond, however, it's way stronger. It's really tough to pull those bonds apart. You have to input significant amounts of energy in order to get those bonds to break. And it's because we're sharing electrons. And so generally we're going to term that a molecular compound. Carbon dioxide is a molecular compound because we have some covalent bonds here. Molecular oxygen is not, because we don't necessarily have a covalently bonded structure. And so in a covalently bonded structure, we're going to see a molecular formula in any bonded structure, really. I shouldn't say covalently, that's misleading. In any bonded structure, any bonded molecule, whether it's a sodium chloride or if it's a carbon dioxide, you're going to have a molecular formula which indicates how many atoms there are and what type of atoms they are. For example, you've got this carbonic acid, which is H2CO3, right? We've got 2 hydrogens, 1 carbon, and 3 oxygens. And all of those are going to be sharing their electrons. They're going to be filling each other's valence shell. And so, you know, that structural formula. Carbon dioxide, we've got a molecular and a structural formula. The structural formula is going to indicate the arrangement of the atoms and how many bonds. So for example, right here with the carbon atom, carbon has a molecular formula, or I shouldn't say that, an atomic number of 6, which means that it has 2 electrons on the innermost electron shell, energy shell, and it's got 4 on the outside, which means that carbon has 4 spaces. So carbon wants 4 more electrons. So carbon can share an electron with 4 other molecule or atoms, I should say, to form a molecule. And so when we look at the carbon dioxide here, what I want you to notice is that we've got oxygen, and oxygen is a little different. Oxygen has 8. It's got an atomic number of 8. And so there's the 2 on the inside, and then there are 6 on the outside. And so oxygen is going to share 2 electrons, 1 and 2, with carbon. It's going to bond twice. It's going to have 2 covalent bonds to carbon right there. It's going to share 2 electrons. And so, you know, carbon shares 2 electrons with oxygen, which fills its outer energy shell, right? Because it only needs 2. There were 6 electrons, and now it's got an extra 2. I'm hoping that you guys are keeping up with this. It is a little bit complicated, but this is not necessarily ridiculously important for you to know. It's important for you to have the base knowledge, but But if you don't understand it completely, it's going to be, you're probably going to be okay. Email me, call me, and we'll talk about it. Anyway, so oxygen, with the 2 electrons that it's sharing with carbon, its outer shell is now filled. It's got 8, right? Now carbon has 6 electrons, 4 of its own and 2 that it's sharing with oxygen. And so, but it really wants 8. It wants to fill that octet, right? And so we get another 2. We come over here and we invite another oxygen to share 2 of its electrons. This oxygen is happy because he gets to share 2 electrons, fill his octet. The carbon is happy because now he's got 4 of the electrons from these 2 oxygens that fill that outer energy shell. And so carbon dioxide is now stable. Carbon dioxide, it doesn't need more electrons, it doesn't need less electrons. It is stable with that extra 4 electrons that it is sharing with the oxygen. I hope this makes sense. If not, then there are 2 things you can do. You can call me and I'll try and walk you through it. Or you can look up some YouTube videos, and there's a couple of YouTube videos that I've got posted already. Anyway, but see the structural formula. So we've got an oxygen on this side of the carbon and an oxygen on this side of the carbon, which allows for different isomers. And an isomer is just going to be a different. It's really just a different arrangement of the atoms around the central atom. So for example, if we were to take this oxygen and move it somewhere, we would have a different isomer of carbon dioxide. And we don't see that too often in some of these really simple molecules, but in some of the more complex ones, we do start to see that. And we certainly see that in some of the simple ones like sugar. Glucose and I believe fructose are different isomers. They're very similar. Oh, no, there's fructose, it's galactose, yeah. I was wondering about that. I said glucose and fructose. I was like, is it fructose or is it galactose? It is galactose. So we've got glucose and galactose, which are different isomers. They've got the same structural formula, right? C6H12O6, C6H12O6, but they're a little bit different. They've got a slightly different arrangement. Yeah, right here. Instead of the H on top and the HO on the bottom, the HO is on top and the H is on the bottom. And you wouldn't think that this would change things all that much, but it can. You know, in your body, your body's going to use galactose, very similar to glucose. They're both sugars. They're both carbohydrates, but it does kind of change the way that the body can break that galactose down because there's some slightly different ways to bind to the galactose than to the glucose. And sort of the same with fructose. Fructose is an isomer because we've got C6H12O6, but way different arrangement here. Rather than the hexagon ring, we've got this pentagon ring. So yeah, covalent bonds, atoms share electrons. We've talked a little bit about that. And it occurs, you see these covalent bonds form when both of the atoms need electrons of some sort. So in our body, we're going to be forming a lot of different bonds with hydrogen, oxygen, nitrogen, and carbon. That's most of the substance of your body is going to be made up of these 4 elements. So, and yeah, the number of covalent bonds that an atom can form is going to be really dependent on how many electrons are in that outermost ring. So, yeah, oxygen needs 2 electrons, and so it can form 2 covalent bonds, like we see in the carbon dioxide, right? We've got the two bonds. And then nitrogen can form 3, carbon can form 4. So, and we do see a single covalent bond where 1 pair of electrons is shared, a double, and a triple. Sometimes we see the triple covalent bond like 2 nitrogen atoms, N2. N2 would be right here. because it's sharing 1, 2, 3 pairs of those electrons, which then fill out that outer shell. So we got 1, 2, and then 3, 4, 5, 6, 7, and 8 on a triple bond. So yeah, carbon needs 4 electrons to satisfy the octet rule. You've got CH4, methane, so there's a carbon and 4 hydrogens on the outside to form that octet. Carbon dioxide, of course, we've got the carbon on the inside, and then we've got the bond right here. We've got a double bond for oxygen and a double bond for another oxygen, which then fills the octet rule. Ethanol, and so really we've got so many different ways that we can form these different molecules using the carbon, which is partly why carbon is so common in the biological field. You see, I mean, we are carbon-based life forms because carbon can form so many different bonds with so many different other molecules. So let's see here, carbon scale, yeah, don't worry about this. Electronegativity, really this electronegativity is going to be the relative attraction of each atom for electrons. Again, you know, it's how many electrons do you need? If you need more electrons, the more electrons you need, the more electronegative you're gonna be. And so 2 atoms of the same element have an equal attraction for electrons. So the resulting bond would be a non-polar covalent bond. But when we're sharing electrons unequally, that's when things get polar. That's when we start to see, let's see here, do we have, I don't have a picture? Okay, let me back up here, back to where we were. When we see unequal sharing of those electrons, we see it actually very commonly in water. Water is going to have a carbon, not a carbon, what am I talking about? A hydrogen and 2 oxygens. It's H2O, an oxygen and 2 hydrogens. It looks like Mickey Mouse. Here, let me change something here. We're going to do a new share. And I'm going to pull up a whiteboard because you guys need to be able to see this. Okay. All right, here we go. I'm going to get a little bit bigger. Can I get this bigger? Yes, I can. There we go. All right. So here is my oxygen. All right. So oxygen, and since we're looking at H2O, we're going to have the 2 H's, the 2 hydrogens. So there's my hydrogen. There's my hydrogen. This is terrible because I have to use a mouse. I wish I had an iPad. If I had an iPad, I could do this way better. So again, it looks like Mickey Mouse. But what I want you to notice here is that hydrogen is sharing 1 of its electrons with oxygen. Well, really, oxygen has a need for 2. It's got a need for 2 electrons. And so these 2 hydrogens are going to donate their electrons, but oxygen is kind of a hog. Oxygen's really big. It's got a large atomic mass compared to hydrogen. And so it actually it holds on to the electrons a little bit more tightly than hydrogen. And so we have an unequal share, which means that hydrogen does not get the electrons as often as oxygen, which means that hydrogen is going to be positive more of the time, and oxygen is going to be negative. And so even though this is 1 molecule, and they are sharing their electrons, we see that on this side of the molecule where the oxygen is, we have a little bit more of a negative attraction. And on this side of the molecule where the hydrogen is, we have a little bit more of a positive attraction. This is polarity right here. We've got the negative pole and the positive pole. And so, you know, oxygen, or water, I should say, water is going to be attracted to anything that is then polar itself. And so if we have another water over here, terrible, my gosh. This side, this positive side, is going to be attracted to this negative side, and the negative side, of course, is going to be attracted to the positive side because of the polarity. And so water sticks to itself. Water has what we call cohesive property, which means that it actually will stick to itself. Water is also adhesive on certain surfaces, like your body. The reason that your hands get wet and stay wet is because your skin is polar. Your skin actually has an attraction to the water molecules, and so the water molecules stick onto your skin. We call these hydrogen bonds. They're very weak bonds, but they're strong enough to hold things together. And because that's holding on, you know, the water is going to stick to your hands. But eventually, the heat from your hands is going to it's going to donate enough energy to cause that water molecule. I'm doing all of this stuff away from the camera. You guys can't see, but it's gonna cause that water molecule to buzz up a little bit. The energy, your body heat, is gonna buzz up that water molecule, and eventually it's going to reach the heat of vaporization, in which it will turn into a gaseous form and float off of your hand, and that's how your hands dry. Your hands are going to dry because they are the water is literally breaking those hydrogen bonds. If you are cold and you don't have very much energy that's making it to the surface of your skin, body heat, then the water will just stay on your hands. It'll just stay stuck to your hands forever, right? And that's certainly something that we notice, is that our hands stay wet longer in a cold environment than they do in a warm environment. So, all right, let's see here. We're going to do new share. Again, we're going to go back over to the lecture PowerPoint here and keep moving along. So, yeah, these are hydrogen bonds. You guys notice that I just buzzed past, you know, this electronegative. You don't need to know any of this stuff for now. Forever. You're never going to need to know this stuff. So, anyway, covalent bonds can be polar or nonpolar. We do see that. A lot of your fats, your lipids, grease, and oil are nonpolar. They don't have any polarity at all, which is why water cannot stick to it. Water rolls right off of a surface that has grease or oil on it because the grease and oil is nonpolar. It can't stick to it. So it's kind of important, and these are sort of important. It's kind of important to understand this polarity in just a minute when we start talking about proteins. So yeah, amphipathic molecules, they're large molecules with both polar and non-polar regions. These guys are weird. They're very odd. The example that we put out there is a phospholipid. Phospholipids are very important to your cells because of the polar and non-polar regions. So let's take a look here. So right here I have just a regular old fat. This is a triglyceride. This is a saturated fat, and this is gonna taste good right here. This is like bacon grease right there. Real tasty and relatively stable. Over here, we've got something a little bit different, right? We've got the phospholipid. So right here we've got 3 fatty acid chains, which is why we call it a triglyceride. Here we have 2 fatty acid chains, one of which has this little double bond right there. Right there. You guys can't see it too well, but right there you're going to have 2 bonds up against that carbon, which means that the hydrogens can no longer be saturated. We're not saturating the whole chain with hydrogens. We've actually added, we've got this extra little double bond, which causes a kink in the tail, which means that this is going to be an unsaturated lipid, which means that it will remain a liquid at room temperature. We'll talk a little bit more about that in a minute. But what's important about this phospholipid is right here, we have a polar region. We've got this glycerol with a phosphate head that is going to be attracted to water. And that attraction to water is going to cause, it's going to cause that side of the phospholipid to stick to things. But over here on this side, we've got this lipid, this non-polar region that is going to be completely repelled by watery sorts of things. And so we can actually form a nice little sheet of cell wall stuff using these phospholipids. So your cell membrane is made up of a double layer of these. New share. Whiteboard. Here we go. Oh, I need to clear this. All drawings. So we've got our phospholipid right here. Okay. There's our two fatty acid chains, the lipid chains, the glycerols, right? And then we've got right up here, we've got the polar region. We've got the phosphoglyceride head. It's the phosphate head right there, which is polar. And so water is going to be attracted to this right here, and it's going to be repelled by this. And so what your body creates in the cells is a double layer where we have the polar head is going to be pointed to the outside of the cell where we have a watery fluid like environment. But then on the other side, we've got this, we've got the same thing going on. It's kind of a mirror of itself. And so on the outside of the cell where it's watery, we can interact with that watery environment because of our polar head. And then on the inside right here, you know, the inside of your cell is also watery and polar. And so the inside of this phospholipid can interact with the intracellular environment. So we got the extracellular environment on the outside, the intracellular environment on the inside. And so we're going to wind up just making a whole bunch of these. We're going to make a sheet of all of these phospholipids. Gosh, this would be easier if I could just do it on an iPad and it would look nicer. We're going to make a whole sheet of these phospholipids all the way around. This, I know this is terrible. You guys are going to have way better pictures coming up later. So there's a whole bunch more. So you're going to have this double layer of phospholipids that then comes all the way around the cell. And it holds the water on the inside of the cell, and it holds the water on the outside of the cell away. But on the inside, we can't get anything through it. If a water molecule wants to go through here, he can't, because there's nothing to hold him in there. These hydro-fearing, these water-fearing tails are going to prevent any water from getting in or out of the cell because they have that non-polar region. Again, if you guys are having a hard time with this, let me know. So let me do new share. So now we're gonna move right along. This is gonna be, I'm already getting a little bit over. So we need to buzz through this a little quicker here. Anyway, intermolecular attractions, these are weak chemical attractions like a hydrogen bond, like I just mentioned, attraction between a partially positive hydrogen atom and a partially negative atom. Individually, they're pretty weak. Collectively, though, they are pretty strong. They, you know, if you get a bunch of them, then they can hold things together pretty well, and they influence how your water molecules behave. So here we've got right here, we've got this polarity, right? We've got the hydrogen right there, we've got the hydrogen right there, and there, and there, and the hydrogen's always going to be a little bit on the positive side, because everything is bigger than a hydrogen. He never gets to play with his electrons. And so he's always going to be just a little bit positive. And so this big negative oxygen can come over here and interact because we're going to have this positive negative attraction right there. And so we've got this glucose that is going to become surrounded by water because the water has this electronegative side that is attracted to the electropositive parts of the glucose that are displayed on the hydrogen. So let me get some other stuff. Van der Waals forces. These are weird. Don't even pay attention to those. We never use van der Waals. That's like more little bit advanced chemistry stuff, like organic chemistry. Hydrophobic interactions. This is where you know the nonpolar regions are actually going to repel any kind of water. We call it hydrophobic or water fearing. So molecular structure of water. Here it is. We've got the Mickey Mouse ears right there. Oxygen in the middle, hydrogens on the sides, and that's going to contribute to all of these different interactions, right? So the hydrogens are going to be attracted to the oxygens on a molecular standpoint, and we're going to form up all of these different little bonds, hydrogen bonds, which contribute to the cohesive nature of water, which is why when you pour water, you can pour it, you can watch it pour because they're all stuck to each other. Imagine for a minute, you know, if I take a jar of sand and I pour the sand, you can see all the individual particles sort of dropping. But imagine for a minute that sand was kind of stuck to itself, right? All of a sudden, it's going to flow out sort of in one piece. And that's what water does. Water is just a whole bunch of particles that's flowing out, but because of those cohesive hydrogen bonding forces, it flows out all kind of in one because they stick to each other. Anyway, 3 phases of water, you know, it's the same as the phases of matter: gas, liquid, and solid. Now, you know, the molecular structure of water sort of makes things, you know, special a little bit. It's really got kind of water has sort of a high, it's got a high temperature of vaporization. You know, you have to get it up to 100 degrees centigrade in order for water to start to vaporize into a gas. And then liquid, it's a liquid at room temperature, which is really weird. We don't see that very often in chemistry. And then at a solid, it's got a fairly low temperature of solidification. Is that the proper term? I'm a biologist, not a chemist. But it's a solid at a fairly low temperature. It's 0 degrees centigrade. And when it is a solid, it's got a really interesting lattice crystal structure that makes it less dense than liquid water, which is also really weird. So, but because of these properties, liquid water can be used in a number of different ways: transportation, lubrication, cushioning, waste removal. It's really handy. Water is really, really handy. Speaking of water, I don't get enough water. So good stuff. Anyway, and then we've got the cohesion and adhesion, the sticking to itself and the sticking to other things. But then it's also got this surface tension, which is sort of the inward pulling of the cohesive forces at the surface of the water. So at the surface, we're actually going to see the water sort of arrange itself and kind of pull itself, pucker itself in, and form kind of this solid skin over the top of the water. You guys have seen soup skin, right? Or pudding skin, I guess. When the soup, the very top of the soup kind of dries out a little bit, and you get that skin on the top. That's what surface tension is. Except it's not really drying out. It's just the molecules of water pulling in. And that's why certain animals can kind of ride on that skin, like a water strider. You guys have seen water striders or water skippers. in the river or in the stream, and they kind of gather up on these still pockets of water, and they just kind of float there, hanging out on top of the water. Well, they're not really floating, they're actually standing on top of the skin. They're standing on top of the surface tension. It's not a floating, it's literally standing on top of the molecules of water. And that actually kind of has some parts to play in the physiology of your lungs. We'll talk about this a little bit later on in AMP2. So anyway, yep, high heat of vaporization, and then a pretty high heat of specific heat. So the amount of energy required to increase the temperature of water, so it's a calorie. 1 calorie is going to be the amount of energy that you need to raise the temperature of 1 gram of water by 1 degree Celsius. So high heat of vaporization, and because it's got a high heat of vaporization, we can remove a lot of heat from the body with sweating or just evaporative cooling in general. In fact, back in the old days, you know, particularly in some of these warmer climates like Thatcher and Safford, Arizona in general. So you know, we're not gonna leave you guys in Globe out either. Globe in Miami, and of course Payson. You know, Payson, we didn't have to worry about that so much because we've got the best weather. But you'd actually put your food in these containers, and then you'd wrap these containers up with towels that you'd soaked in the water, and as the wind and as the sun would evaporate the water, that evaporating water would suck so much moisture out of these cooling containers that it would cool off your milk enough to keep it good for a little bit longer. So, you know, some little tricks that they used to do. And of course, we still use evaporative cooling in our homes, the swamp cooler. I have a swamp cooler in my house in Payson because I don't need an air conditioning unit because the weather here is so great. Anyway, Payson's okay. It's got nice weather, but that's about it. Anyway, you can actually do a lot of cooling. I mean, I can get my house pretty dadgum cold by running that swamp cooler. So water is also a universal solvent, which means that pretty much everything dissolves in water. You put anything in water for long enough and it's going to dissolve. So and then yeah, we get sort of this hydrophilic and hydrophobic. Hydrophilic means water loving, hydrophobic means water fearing. And some of these substances, you know, the hydrophilic polar molecules are going to have a tendency to dissolve in water. So some substances can dissolve, but they'll remain intact, like glucose and alcohol, but these are molecules. And so non-electrolytes remain intact, but do not conduct a current. That's going to be like glucose and alcohol. Electrolytes like salt, you know, sodium, potassium, lithium, those electrolytes are actually going to be used to, they can conduct an electrical current. So anyway, we've already talked about hydrophobic, but we're talking about like fats and oils. These are non-polar, and so water does not stick to them, which means that we term them hydrophobic. Let's see here. Yeah, then amphipathic molecules are kind of important. Phospholipid molecules. Let's look at these guys really quick here. So I've got a nice picture. So here's our nice little picture of a phospholipid membrane. Right there. Note that we have on the top, we've got the hydrophilic head, the water-loving head, the polar head, which can interact with all the water molecules in the extracellular space, the outside of the cell. And then again on this side, because it's a double layer, because we've got the bilayer going on here with the tails pointing in, the intracellular space, these polar regions can interact with the water on the inside of the cell. But right here in the middle, right here in between, we've got a hydrophobic region right there. non-polar region, which does not let anything through it. If the water tries to get through that, it can't get through it because of that non-polar region. It's constantly repelling the water. And this actually kind of brings me to another very important sort of biological function that you guys will be learning about in microbiology. If we can take that phospholipid bilayer, and if we can somehow break apart those phospholipids and allow the inside of the cell to go on the outside of the cell, that's a really good way of killing a cell. So if we're talking about like bacterial diseases, all we've got to do with that bacteria is break apart the phospholipid bilayer, the cell membrane, and all of a sudden, bacteria dead. So you're going to learn about some drugs that do that in your microbiology course. Anyway, then we've got this little micelle here. Micelles are going to be little droplets, teeny tiny little droplets of fats where all of the tails sort of point into themselves, and you wind up with this little droplet of oil. And this is what we do when we emulsify things. We're gonna take that big glob of fat, and we're gonna change it into a bunch of teeny tiny little micelles that can then float around in the water. If you take water and oil, put it in a jar, and you just shake the absolute crap out of it, you can actually sort of see some emulsification occurring, in which you'll see these tiny little droplets become sort of interspersed throughout the water. Now, oil is liquid enough that it can kind of come back together very quickly. But we do see that in like mayonnaise. Mayonnaise is actually, it's an emulsification of egg whites and oil. That's really all it is. And so the white structure, the white color of the mayonnaise is just all of the teeny tiny little droplets of oil or fat that are suspended in the egg white and reflecting the light in a certain way. Again, if you take that oil and water, you shake it up really good, you're actually going to see the color change a little bit from sort of a nice little golden color of your oil to more of this kind of grayish approaching white. And if you were to shake it up enough and emulsify it, all those little droplets of oil would reflect the light in such a way to color it white. Man. We still got some ways to go. So if you need a break, now's a good time to take a break. Actually, you can take a break anytime. Just hit pause and go get you something to eat. If you are feeling right now a little bit overwhelmed, a little bit, oh my gosh, this is a lot to take in, please go ahead and hit that pause and go get you something relatively sweet. Like a little small piece of chocolate. A small piece of chocolate works really good. Eat that up, maybe eat 2 or 3. I'm actually probably gonna run out and get me some chocolate here in just a minute. And that will actually, the glucose in that chocolate's gonna give you a little bit of a bump in your energy. Might be good for another 20 minutes or so. So go ahead and get that done, or just go get some lunch. And we're gonna continue with water being a neutral solvent. Water can spontaneously dissociate to form ions. It's kind of interesting how it does that. But when this happens, we wind up with these positive hydrogen ions and negative hydroxyl ions. But it stays neutral, right? We're gonna remain neutral as far as pH goes. I've got a call coming in, so I am going to pause this really quick. Let's see here more.